Right now, as you're watching this video, you're experiencing the universe in the most ordinary way imaginable. Light travels from your screen to your eyes at exactly 299,792,458 meters per second. Time ticks forward at its steady pace. Space extends around you in three familiar dimensions. But what if I told you that hidden within Einstein's equations lies a possibility so extraordinary it could revolutionize everything we know about travel, communication, and our place in the cosmos? Tonight, we're diving into one of the most mind-bending concepts in theoretical physics, a phenomenon that could allow you to step through a doorway in New York and emerge instantly on the other side of the galaxy. We're talking about wormholes and the tantalizing question that has captivated physicists for nearly a century. Can we ever build one? Picture this scene from 1935. Albert Einstein, already the most famous scientist in the world, sits in his Princeton office alongside his colleague, Nathan Rosen. They're not working on anything as mundane as atomic theory or quantum mechanics. Instead, they're wrestling with the implications of Einstein's own general theory of relativity, published 20 years earlier. The equations that describe how massive objects warp the fabric of spacetime itself have revealed something unexpected, something that even Einstein finds difficult to believe. Their calculations suggest that under very specific conditions, spacetime could fold back on itself, creating tunnel-like structures that connect distant regions of the universe. These hypothetical bridges through the cosmos would later be called wormholes, but Einstein and Rosen initially viewed them as mathematical curiosities rather than practical transportation devices. They were trying to develop a unified field theory that could explain elementary particles as topological features of spacetime itself. What they discovered instead was far more profound. The Einstein-Rosen bridge, as it came to be known, represented the first rigorous mathematical description of what we now call a traversable wormhole. But there was a problem, a fundamental flaw that would plague wormhole physics for decades to come. These bridges were catastrophically unstable, collapsing faster than light itself could travel through them. To understand why this matters, we need to grasp the basic physics of how wormholes would theoretically function. Imagine spacetime not as empty void, but as a flexible fabric that can be stretched, compressed, and folded. Massive objects like stars and planets create dents in this fabric, which we experience as gravity, but Einstein's equations allow for more exotic configurations, geometries where the fabric curves back on itself to create shortcuts through higher dimensions. The easiest way to visualize this concept involves a simple thought experiment with a sheet of paper. Draw 2 points on opposite sides of the sheet, representing distant locations in space. In normal circumstances, traveling between these points requires covering the entire distance along the surface of the paper. But fold the paper so the 2 points touch, and suddenly you have a direct connection that bypasses the normal constraints of distance. This is essentially how a wormhole would function, creating a bridge through higher dimensional space that allows near instantaneous travel between distant regions. The mathematical elegance of this concept is breathtaking, but the physical requirements are staggering. Creating such a structure would require manipulating space-time itself on scales never before attempted by human technology. We're not talking about building a machine or constructing a device, we're talking about engineering the fundamental geometry of reality. The instability problem that Einstein and Rosen discovered stems from a basic principle of general relativity. Spacetime naturally wants to minimize its curvature, much like a stretched rubber sheet wants to return to its flat state. Any tunnel through spacetime would experience tremendous pressure to collapse, pinching off the connection before anything could pass through. The mathematics are unforgiving. Even light, traveling at the fastest possible speed, cannot traverse an Einstein-Rosen bridge before it collapses. This fundamental challenge seemed to doom the concept of practical wormhole travel until the 1960s, when Princeton physicist John Archibald Wheeler began to study these structures in earnest. Wheeler, who coined the term wormhole by comparing their geometry to the hole a worm might bore through an apple, recognized that while Einstein-Rosen bridges were unstable, they represented only one possible solution to the field equations. Perhaps other configurations might prove more stable. Wheeler's work laid the foundation for decades of theoretical research into exotic spacetime geometries. But it wasn't until the 1980s that a breakthrough occurred that would transform our understanding of traversable wormholes. The catalyst was an unexpected request from Carl Sagan, who was writing his novel Contact and needed a scientifically plausible method for interstellar travel. Sagan approached Kip Thorne at Caltech, asking whether the laws of physics might permit some form of faster-than-light travel. Thorne, one of the world's leading experts on general relativity, initially dismissed the idea. But as he began working through the mathematics with his student Michael Morris, they made a remarkable discovery. Under very specific conditions, the Einstein field equations do permit stable, traversable wormholes. The catch was that such structures would require something that had never been observed in nature: exotic matter. Exotic matter represents one of the most challenging concepts in theoretical physics. Unlike the ordinary matter that makes up stars, planets, and everything we can see and touch, exotic matter would possess negative energy density and negative pressure. This isn't simply matter moving backward in time or antimatter, which has positive energy density. Exotic matter would need to violate fundamental energy conditions that ordinary matter always obeys. The concept challenges our deepest intuitions about how the universe works. In our everyday experience, energy density and pressure are always positive quantities. A compressed gas has positive pressure pushing outward. A massive object has positive energy density that creates gravitational attraction, but exotic matter would behave in the opposite way, creating repulsive gravitational effects that could counteract the natural tendency of a wormhole to collapse. Think of it this way: ordinary matter tells spacetime to curve inward, creating the attractive force we experience as gravity. Exotic matter would tell spacetime to curve outward, creating a repulsive effect that could keep a wormhole throat open against the crushing forces that would otherwise destroy it. The mathematics work beautifully, but finding or creating such matter represents a challenge that may be insurmountable. The energy requirements alone are staggering. Thorne's calculations suggest that stabilizing even a 1-meter-wide wormhole would require exotic matter with negative energy equivalent to the mass of Jupiter. That's nearly 2 × 10⁻27 kilograms of matter, with properties that may not exist anywhere in the universe. Even more optimistic calculations by other physicists still require exotic matter with energy equivalent to a supernova explosion. But perhaps the most troubling aspect of exotic matter isn't its energy requirements, but its apparent violation of causality itself. If exotic matter with negative energy density could be concentrated in sufficient quantities, it might enable violations of the second law of thermodynamics. Energy could flow from cold objects to hot objects without external work being performed. Effect could precede cause. The fundamental arrow of time that gives structure to physical processes could be reversed. These causality violations aren't just theoretical concerns. They represent potential paradoxes that could unravel the logical consistency of physics itself. If wormholes could be used for backward time travel, as some theoretical models suggest, they might enable paradoxes where effects occur before their causes. A traveller could theoretically journey back in time and prevent their own departure, creating logical impossibilities that have no resolution within our current understanding of physics. Yet despite these seemingly insurmountable challenges, exotic matter may not be entirely fictional. Quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, does predict phenomena that seem to violate classical energy conditions. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 demonstrates that quantum field fluctuations can create regions of negative energy density under very specific conditions. The Casimir effect occurs when two uncharged conducting plates are placed extremely close together in a vacuum. The quantum fields between the plates are constrained in ways that suppress certain wavelengths of virtual particle fluctuations. This creates a region where the energy density is actually less than that of empty space, resulting in a measurable attractive force between the plates. While this effect has been experimentally verified many times, the quantities of negative energy involved are minuscule compared to what wormhole construction would require. The gap between what quantum mechanics provides and what wormhole physics demands represents one of the fundamental obstacles to practical wormhole construction. While the Casimir effect proves that negative energy densities can exist in nature, scaling these effects up to macroscopic levels would require techniques and technologies that remain purely speculative. We would need to manipulate quantum fields on scales billions of times larger than anything currently possible. Recent theoretical work has explored whether alternative approaches might circumvent some of these limitations. Some physicists have investigated whether quantum field fluctuations in curved spacetime might naturally provide the exotic matter needed for wormhole stabilization. Others have examined whether modifications to general relativity itself might permit stable wormholes without requiring exotic matter at all. These investigations have led to increasingly sophisticated models of hypothetical wormhole geometries. The Morris-Thorne wormhole, developed in the late 1980s, provided the first mathematically rigorous framework for understanding how a traversable wormhole might function. Their solution described a spherically symmetric wormhole with specific geometric properties that would allow safe passage while minimizing the amount of exotic matter required for stability. But even the most optimistic theoretical models face fundamental constraints imposed by quantum gravity effects. As we probe deeper into the nature of spacetime at the smallest scales, we encounter phenomena that our current theories cannot adequately describe. At distances approaching the Planck length, roughly 10 to the minus 35 meters, the smooth geometry of classical spacetime breaks down into what physicists call quantum foam. In this realm, the very concept of distance and time becomes uncertain, fluctuating according to quantum mechanical principles. Virtual particles pop into existence and annihilate in timeframes so brief that they exist below the threshold of direct observation. The energy densities involved in these fluctuations are enormous, potentially affecting the stability of any macroscopic wormhole in ways we cannot predict with current theory. The challenge of quantum gravity represents perhaps the deepest mystery in modern physics. We have two incredibly successful theories: general relativity, which describes gravity and the large-scale structure of spacetime, and quantum mechanics, which governs the behavior of matter and energy at microscopic scales. But these theories are fundamentally incompatible when applied to situations involving both strong gravitational fields and quantum effects. If you find yourself drawn to these cosmic puzzles, I'd be grateful if you gave this video a like and perhaps subscribe. Wormhole construction would inevitably require understanding physics in precisely this regime, where both quantum mechanics and general relativity become important. The exotic matter needed for wormhole stabilization would need to be concentrated to densities where quantum effects become significant. The spacetime curvature around the wormhole throat would be so extreme that quantum field fluctuations could dramatically affect the geometry itself. Without a unified theory of quantum gravity, our understanding of wormhole physics remains necessarily incomplete. String theory, loop quantum gravity, and other approaches to quantum gravity each make different predictions about what might be possible in terms of spacetime engineering. Some suggest that fundamental limits might prevent the existence of traversable wormholes entirely. Others indicate that exotic phenomena, like wormholes, might be not only possible, but inevitable features of quantum spacetime. The implications extend far beyond academic physics into questions that touch the very foundations of reality itself. If traversable wormholes could be constructed, they would represent the ultimate triumph of intelligence over the constraints of space and time. Distant galaxies would become as accessible as neighboring cities. The universe would shrink from an impossibly vast realm, requiring millions of years to explore into a connected network of accessible worlds. But the challenges we've explored represent only the beginning of the obstacles that would need to be overcome. The engineering requirements for wormhole construction would dwarf any technological project ever attempted by human civilization. We would need to master the fundamental forces of nature at levels that make our current understanding seem primitive by comparison. The story takes an even more dramatic turn when we consider the specific engineering challenges that would face any civilization attempting to construct a working wormhole. Beyond the seemingly impossible requirement for exotic matter, the geometric precision needed to create a stable spacetime tunnel defies imagination. We're talking about manipulating the curvature of spacetime itself, with tolerances that would make precision engineering on atomic scales seem crude by comparison. Consider the throat of a wormhole, the narrowest section where the tunnel connects two distant regions of space. This throat must maintain a precise geometric configuration that prevents it from pinching off, while simultaneously allowing matter and energy to pass through safely. The space-time curvature in this region would be so extreme that even tiny fluctuations could cause catastrophic collapse or create deadly tidal forces that would tear apart anything attempting passage. The mathematics reveal just how unforgiving these constraints are. The metric tensor, which describes the geometry of spacetime around the wormhole, must satisfy incredibly specific conditions. Any deviation from these exact values, even at the level of quantum fluctuations, could destabilize the entire structure. It's like trying to balance a pencil on its point while standing on a ship during a storm, except the pencil represents the fabric of reality itself, and the storm consists of quantum uncertainty fluctuations that operate at the deepest level of physical law. But let's assume for a moment that some advanced civilization has somehow overcome these obstacles. They've discovered a way to create or harvest exotic matter in macroscopic quantities. They've developed technologies capable of manipulating spacetime geometry with quantum-level precision. They've constructed a stable, traversable wormhole connecting 2 points in space. What would it actually be like to travel through such a structure? The journey would be unlike anything in human experience. As you approach the wormhole mouth, spacetime itself would appear distorted around you. Light from distant stars would be bent and twisted by the extreme gravitational fields, creating visual effects that would strain the limits of perception. The wormhole entrance might appear as a sphere hanging in space, its surface showing not reflection but a view of the destination on the other side of the galaxy. Stepping through would involve passing from one region of spacetime to another through a tunnel that exists partially outside our normal three-dimensional reality. The transit time could be measured in seconds or minutes, regardless of the astronomical distances being covered. But this apparent simplicity masks profound complexities that arise from the relativistic effects governing the wormhole's behavior. Time dilation would play a crucial role in determining the practical utility of wormhole travel. If the two mouths of the wormhole are moving relative to each other, or exist in regions with different gravitational potentials, time would pass at different rates at each end. A traveller might emerge from the wormhole to find that while their journey took only minutes, years, or decades had passed in the outside universe. The implications for maintaining any kind of coherent civilization across wormhole networks would be staggering. Even more troubling is the possibility that wormholes could become time machines. If one mouth of a wormhole were accelerated to high speeds and then reconnected with its stationary partner, the time dilation effects would create a situation where the two ends exist at different times. Travel through such a wormhole would not just transport you through space, but through time itself, potentially allowing journeys into the past. This temporal aspect of wormhole physics opens up paradoxes that have haunted theoretical physicists for decades. The grandfather paradox, where a time traveler prevents their own birth, represents just one example of the logical impossibilities that closed time-like curves might create. Some physicists have proposed that the universe might have built-in mechanisms to prevent such paradoxes, perhaps through quantum effects that would destroy any wormhole before it could enable backward time travel. The Novikov self-consistency principle suggests that the laws of physics might somehow conspire to ensure that only self-consistent timelines are possible. Under this interpretation, any attempt to change the past would be thwarted by quantum mechanical effects or other physical processes that preserve the logical structure of causality. But proving or disproving such principles would require experimental access to the very phenomena they're designed to explain. Recent developments in quantum information theory have added new layers of complexity to our understanding of wormhole physics. The discovery of quantum entanglement and its apparent ability to create instantaneous correlations between distant particles has led some physicists to wonder whether entanglement and wormholes might be fundamentally related phenomena. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that every pair of entangled particles might be connected by a microscopic wormhole. This idea represents a profound shift in how we think about the relationship between quantum mechanics and general relativity. If quantum entanglement is indeed equivalent to geometric connections through higher dimensional space, then the quantum mechanical correlations we observe in laboratory experiments might be evidence that wormhole-like structures already exist at the microscopic level throughout the universe. The implications extend to recent experiments that claim to have created wormholes in quantum computers. While these experiments don't create actual space-time tunnels, they do demonstrate that quantum information can be transferred through systems that exhibit wormhole-like behavior in their mathematical description. The debate over whether these quantum simulations truly represent wormholes or merely mathematical analogies continues to divide the physics community. But even if microscopic quantum wormholes permeate the universe, scaling them up to macroscopic sizes suitable for travel would require overcoming the same fundamental obstacles that plague all wormhole construction schemes. The energy requirements grow exponentially with the size of the wormhole, and the stability constraints become increasingly difficult to maintain as quantum effects interact with the large-scale geometry of spacetime. The tidal forces that would affect anything passing through a wormhole present another formidable challenge. Just as the moon's gravity creates tides in Earth's oceans, the extreme spacetime curvature around a wormhole throat would create differential gravitational effects that could stretch and compress any object attempting passage. For a human traveler, these forces could range from uncomfortable to lethal, depending on the specific geometry of the wormhole. Theoretical calculations suggest that minimizing tidal forces would require wormholes with very specific geometric properties. The throat would need to be relatively wide compared to its length, and the transition from normal spacetime to the wormhole interior would need to be extremely smooth. But achieving such geometries would require even more exotic matter and even more precise engineering than simpler wormhole designs. The radiation environment inside a wormhole presents additional hazards that would need to be addressed by any practical design. As matter and energy pass through the tunnel, they would interact with the exotic matter lining the throat, potentially creating high-energy particles and electromagnetic radiation. The blue shifting of light as it falls into the gravitational field of the wormhole mouth could concentrate ordinary starlight into deadly gamma rays that would sterilize anything attempting passage. These radiation effects become particularly severe when we consider the quantum field fluctuations that would inevitably occur in the extreme environment of a wormhole throat. Virtual particles, normally too short-lived to have observable effects, could be amplified by the intense gravitational fields into real particles with substantial energies. The resulting cascade of particle creation and annihilation could make the interior of a wormhole uninhabitable, even if all other engineering challenges were somehow overcome. The construction process itself would represent an unprecedented feat of cosmic engineering. Unlike building a bridge or constructing a space station, creating a wormhole would require manipulating the fundamental structure of spacetime across potentially astronomical distances. The exotic matter would need to be precisely positioned and maintained in configurations that violate our normal understanding of how matter and energy behave. Some theoretical models suggest that wormholes might be constructed by manipulating black holes, using their extreme gravitational fields to curve spacetime into the desired geometry. But this approach would require technologies capable of safely approaching and manipulating objects whose gravitational fields are so intense that they trap light itself. The engineering challenges involved in working near the event horizon of a black hole boggle the imagination. Alternative approaches might involve creating artificial spacetime curvature using exotic forms of energy we haven't yet discovered. Some speculative theories suggest that vacuum fluctuations could be manipulated to create the negative energy densities needed for wormhole construction, but the energy requirements for such manipulation would likely exceed the total energy output of entire stars. The materials science challenges alone would revolutionize our understanding of matter and energy. Any structure capable of surviving the extreme conditions inside a wormhole would need properties unlike anything found in nature. The exotic matter itself would need to maintain its unusual properties under conditions of extreme stress, temperature, and radiation that would instantly vaporize any known material. Even if all these technical obstacles could somehow be overcome, the social and economic implications of wormhole technology would be staggering. The ability to travel instantly between distant points in space would fundamentally transform human civilization, making interstellar colonization as routine as international air travel. But the energy costs involved in wormhole construction and maintenance might limit access to only the most advanced and wealthy civilizations. The strategic implications would be equally profound. Any nation or organization with access to wormhole technology would possess unprecedented advantages in terms of transportation, communication, and resource access. The geopolitical consequences of such asymmetric capabilities could reshape the balance of power on Earth and beyond in ways that are difficult to predict. Yet despite these overwhelming challenges, the theoretical possibility of wormhole construction continues to drive research in fundamental physics. Every advance in our understanding of quantum gravity, exotic matter, and spacetime geometry brings us marginally closer to understanding whether such structures could ever be more than mathematical curiosities. The questions raised by wormhole physics touch on the deepest mysteries of reality itself, forcing us to confront the limits of what might be possible in a universe governed by quantum mechanical and relativistic laws. The journey from theoretical possibility to practical implementation would require not just technological advances, but fundamental breakthroughs in our understanding of the nature of space, time, matter, and energy. We would need to develop a complete theory of quantum gravity, master the creation and manipulation of exotic matter, and solve engineering challenges that dwarf anything ever attempted in human history. But perhaps the most important question isn't whether we can build a wormhole, but whether we should. The same technologies that might enable wormhole construction could potentially destabilize the fabric of spacetime itself, creating consequences that extend far beyond our ability to predict or control. We're not just talking about building a new form of transportation, but about fundamentally altering the structure of reality in ways that could affect the entire universe. The paradoxes multiply when we examine what happens to causality itself in a universe where wormholes exist. Einstein's special theory of relativity established that simultaneity is relative. Events that appear simultaneous to one observer may occur at different times for another observer moving at high speed. But wormholes could shatter even this flexible understanding of temporal order, creating scenarios where cause and effect become hopelessly tangled. Imagine a wormhole where one mouth orbits close to a massive star while the other floats in empty space. The gravitational time dilation near the star would cause time to pass more slowly at that mouth compared to its distant partner. After years of this differential aging, the two mouths would exist at effectively different times. A message sent through the wormhole from the space-bound mouth to the star-bound mouth would arrive in that mouth's past, potentially allowing information to influence its own origin. This isn't just a philosophical puzzle. Such closed time-like curves could enable violations of causality that would undermine the logical structure of physics itself. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics somehow prevent the formation of closed time-like curves. According to this idea, any attempt to create a time machine would be automatically thwarted by quantum effects that destroy the mechanism just before it becomes operational. The quantum fluctuations that permeate empty space might serve as nature's immune system against temporal paradoxes. As spacetime curves approach the configuration needed for backward time travel, virtual particles would be blue-shifted to infinite energies, creating a wall of destructive radiation that would obliterate any incipient time machine. These quantum effects represent the universe's way of protecting its own logical consistency. But Hawking's conjecture remains unproven, and some physicists argue that closed time-like curves might be not only possible, but necessary features of a complete theory of quantum gravity. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe as a whole, permits solutions that include closed causal loops. These mathematical structures suggest that causality violations might be fundamental aspects of reality at the deepest level, hidden from our everyday experience by the classical behavior of macroscopic objects. Recent work in quantum information theory has revealed even stranger possibilities. The concept of quantum superposition, where particles exist in multiple states simultaneously until observed, might extend to causal relationships themselves. In a quantum universe, events might exist in superpositions of different causal orders, with cause and effect remaining indefinite until some form of quantum measurement collapses the system into a definite configuration. These quantum causal indefinitenesses have been demonstrated in laboratory experiments using photons and quantum circuits. While these experiments don't involve actual time travel, they show that our classical understanding of causality breaks down at the quantum level in ways that could have profound implications for wormhole physics. If spacetime itself is subject to quantum uncertainty, then the very notion of a well-defined wormhole geometry might be fundamentally flawed. The challenge of quantum gravity becomes unavoidable when we consider the extreme conditions that would exist near a wormhole throat. The energy densities of exotic matter required for stabilization would approach or exceed the Planck density, roughly 10 to the 94th kilograms per cubic meter. At these densities, the classical description of spacetime provided by general relativity breaks down completely, and quantum gravitational effects become dominant. String theory, one of the most promising approaches to quantum gravity, suggests that spacetime might not be fundamentally smooth but composed of tiny vibrating strings existing in higher dimensional space. These strings would interact according to quantum mechanical rules that could dramatically alter the behavior of exotic matter and the stability of wormhole geometries. Some string theory models predict that wormholes might be naturally unstable due to quantum corrections that weren't accounted for in classical general relativity. Loop quantum gravity offers a different perspective. suggesting that spacetime itself might be quantized at the smallest scales, composed of discrete units of area and volume, rather than the smooth continuum assumed by classical physics. In this picture, the throat of a wormhole would be built from quantum geometric building blocks, whose properties might fundamentally limit the kinds of structures that can exist. The holographic principle, which emerged from studies of black hole physics, adds another layer of complexity to our understanding of wormhole construction. This principle suggests that all the information contained in a volume of space can be encoded on its boundary surface, implying that spacetime might be fundamentally two-dimensional rather than three-dimensional. If this principle applies to wormholes, then the interior geometry of the tunnel might be entirely determined by information encoded on its entrance and exit surfaces. These holographic ideas have led to surprising connections between wormhole physics and quantum entanglement. The ADS-CFT correspondence, a mathematical relationship between gravity theories and quantum field theories, suggests that certain types of wormholes might be equivalent to quantum entangled systems. In this picture, creating a wormhole would be equivalent to establishing quantum entanglement between distant regions of space, providing a potential pathway for wormhole construction that doesn't require exotic matter. But even these quantum approaches face formidable obstacles. The energy scales involved in quantum gravity are so extreme that they dwarf anything accessible to current or foreseeable technology. The Planck energy, the scale at which quantum gravitational effects become important, is roughly 10 to the 19th billion electron volts. For comparison, the most powerful particle accelerators on Earth reach energies of only about 10 trillion electron volts, falling short by a factor of a billion. The technological gap extends far beyond energy scales to encompass our fundamental understanding of how quantum gravity operates. We don't yet have a complete theory that successfully unifies quantum mechanics and general relativity. Without such a theory, our predictions about wormhole behavior remain necessarily speculative. We're attempting to engineer structures that require understanding physics we haven't yet discovered. The information paradox that plagues black hole physics extends to wormhole construction as well. If information cannot be destroyed, as quantum mechanics suggests, then what happens to information that enters a wormhole? Does it emerge unchanged at the other end? Is it somehow duplicated or scrambled in ways that violate the fundamental principles of quantum mechanics? These questions touch on the deepest mysteries of how information and spacetime are related. Recent proposals have suggested that wormholes might serve as cosmic information channels, allowing quantum information to be transmitted across vast distances without violating the speed of light limit. But such proposals require exotic matter configurations that are even more speculative than those needed for classical wormhole construction. The quantum error correction needed to maintain information fidelity through a wormhole would require control over quantum systems at a level that exceeds our current capabilities by orders of magnitude. The thermodynamic properties of wormholes present additional puzzles that highlight the deep connections between gravity, quantum mechanics, and information theory. If wormholes can be assigned temperatures and entropies like black holes, then their construction and operation would need to respect the laws of thermodynamics. The second law of thermodynamics, which requires that entropy never decrease in isolated systems, might impose fundamental limits on what kinds of wormhole operations are possible. Some theoretical calculations suggest that the process of sending matter or information through a wormhole would necessarily increase the total entropy of the universe, potentially making such operations thermodynamically expensive beyond any practical implementation. The energy cost of entropy production might dwarf even the enormous energy requirements for exotic matter creation and spacetime manipulation. The firewall paradox, which arose from attempts to resolve the black hole information paradox, might have analogous implications for wormhole physics. If quantum effects create firewalls of high-energy particles at event horizons, Similar effects might occur at wormhole throats, making them lethal to any traveller, regardless of how carefully they are engineered. The resolution of these paradoxes might require fundamental revisions to our understanding of spacetime, quantum mechanics, or both. But perhaps the most profound challenge facing wormhole construction lies not in the realm of theoretical physics, but in the practical engineering required to implement any viable design. Even if we assume that all theoretical obstacles can be overcome, the scale of the construction project would be unprecedented in human history. We would need to manipulate matter and energy on scales that span from subatomic particles to astronomical distances. The precision required for wormhole construction makes the most demanding engineering projects on Earth look simple by comparison. The James Webb Space Telescope, one of the most precise instruments ever built, maintains alignment between its mirrors to within a fraction of the wavelength of light. But wormhole construction would require controlling the geometry of spacetime itself to within a fraction of the Planck length, the smallest distance scale at which the concept of distance has any meaning. The materials science challenges would revolutionize our understanding of condensed matter physics. Any structural components that support a wormhole would need to withstand stresses that exceed the tensile strength of atomic nuclei. The exotic matter itself would need to maintain its unusual properties under conditions of extreme curvature, temperature, and radiation that would instantly destroy any known form of matter. The power requirements alone would challenge the energy resources of an entire civilization. Some calculations suggest that maintaining a human-sized wormhole would require continuous power input equivalent to the total energy output of multiple stars. The infrastructure needed to generate, distribute, and control such enormous energy flows would itself represent a technological achievement that dwarfs any current human capability. Quality control and safety protocols for wormhole construction would need to account for failure modes that could potentially damage the fabric of spacetime itself. A catastrophic failure during construction might not simply destroy the wormhole, but could create spacetime defects that persist indefinitely, potentially affecting the entire region of the galaxy. The risk assessment for such a project would need to consider consequences that extend far beyond the immediate construction site. The regulatory and governance challenges would be equally daunting. Who would have the authority to approve wormhole construction? How would international law adapt to address structures that could connect any point on Earth to any other point in the universe? The geopolitical implications of wormhole technology would require unprecedented levels of international cooperation and oversight. Environmental impact assessments would need to consider effects that extend across cosmic scales. The gravitational waves generated by wormhole construction might be detectable across the galaxy, potentially interfering with other civilizations or natural processes. The exotic matter required for construction might need to be harvested from natural sources, depleting cosmic resources in ways that could affect the long-term evolution of the universe itself. Even the most optimistic scenarios for wormhole construction would require development timelines measured in centuries or millennia. The fundamental research needed to understand quantum gravity and exotic matter would itself represent a generational project requiring sustained international collaboration. The technological infrastructure needed to support such research would require economic resources comparable to entire national budgets. The human factors involved in wormhole travel would present psychological and physiological challenges that extend beyond the technical requirements for construction. The experience of instantaneous travel across cosmic distances would be unlike anything in human evolutionary history. The psychological adaptation required to function in a universe where distance becomes meaningless might exceed our species' capacity for adjustment. The social implications would be equally profound. Wormhole technology would create unprecedented opportunities for cultural exchange and resource sharing, but it could also enable new forms of conflict and exploitation. The same tunnels that connect distant worlds for peaceful purposes could become conduits for invasion or economic domination. The balance between the benefits and risks of such technology would require wisdom that matches its technological sophistication. The economic models that govern human civilization would need fundamental revision in a universe where transportation costs become negligible. Traditional concepts of scarcity and distance that underpin market economics would become obsolete. The resulting social and economic disruptions might be more challenging to navigate than the technical obstacles to wormhole construction itself. Yet despite these overwhelming challenges, the theoretical possibility of wormhole construction continues to drive research at the frontiers of physics. Each advance in our understanding of quantum gravity, exotic matter, and the fundamental structure of spacetime brings us marginally closer to understanding whether such ambitious projects could ever move beyond the realm of speculation into practical engineering. The questions raised by wormhole physics touch on the most fundamental aspects of reality. They force us to confront the limits of what might be possible in a universe governed by quantum mechanical and relativistic principles. They challenge us to think beyond the constraints of our current technological capabilities and consider what kinds of cosmic engineering projects might be undertaken by civilizations with access to physics we have yet to discover. The pursuit of wormhole technology represents humanity's deepest aspirations to transcend the limitations imposed by space and time. Whether such aspirations can ever be realized remains one of the most profound open questions in science. The answer will depend not just on advances in theoretical physics and engineering, but on our capacity to develop the wisdom needed to wield technologies that could reshape the structure of reality itself. The universe keeps its deepest secrets closely guarded, revealing them only to those willing to push the boundaries of knowledge into realms where mathematics and imagination converge. Wormhole construction represents the ultimate test of whether intelligence can triumph over the fundamental constraints that govern cosmic evolution. The outcome of this test will determine whether the vast distances between stars remain permanent barriers to exploration, or become merely the first obstacles to be overcome on humanity's journey toward true cosmic citizenship. The mathematics that govern our universe contain hidden doorways to possibilities that stretch the imagination beyond its limits. Tonight, as quantum computers around the world attempt to simulate the behavior of hypothetical spacetime tunnels, we're witnessing humanity's first tentative steps toward understanding whether the cosmos itself might be engineered. Recent experiments at Google's quantum computing facility have created what researchers cautiously describe as holographic wormholes. These aren't actual tunnels through spacetime, but rather quantum information systems that exhibit mathematical properties analogous to gravitational wormholes. The distinction matters enormously, yet these experiments represent something unprecedented. The first time humans have successfully modeled wormhole-like behavior in a controlled laboratory environment. The quantum computer used in these experiments manipulates information in ways that mirror how gravity might behave in higher dimensional spaces. When quantum bits of information are entangled and then manipulated according to specific protocols, they create information pathways that share mathematical similarities with spacetime tunnels. The information doesn't travel faster than light, but it does traverse the quantum system in ways that suggest deep connections between quantum mechanics and gravitational physics. These experiments emerge from a profound theoretical insight known as the holographic principle. This principle suggests that all the information contained in a volume of space can be encoded on its boundary surface, much like a hologram encodes three-dimensional images on a two-dimensional surface. If spacetime itself operates according to holographic principles, then the interior of a wormhole might be entirely determined by quantum information encoded on its entrance and exit surfaces. The implications ripple through our understanding of reality in waves that are still being felt throughout the physics community. Juan Maldacena and Leonard Susskind proposed that quantum entanglement, the mysterious connection that allows particles to instantly influence each other across vast distances, might be equivalent to microscopic wormholes connecting those particles. Their ER equals EPR conjecture suggests that every entangled pair of particles shares a tiny geometric bridge through higher dimensional space. If this conjecture proves correct, then quantum entanglement, which we can create and manipulate in laboratories around the world, represents evidence that wormhole-like structures already permeate the universe at microscopic scales. The challenge would shift from creating wormholes to scaling them up, from quantum dimensions to sizes that could accommodate macroscopic objects or even human travelers. But scaling quantum effects to macroscopic dimensions has historically proven to be one of the most challenging problems in physics. Quantum coherence, the delicate quantum mechanical properties that enable entanglement and superposition, typically survives only in carefully isolated systems at extremely low temperatures. The moment quantum systems interact with their environment, decoherence destroys the very properties that make quantum effects possible. Extending quantum wormholes to macroscopic scales would require maintaining quantum coherence across distances and energy scales where such coherence has never been observed. We would need to protect quantum information from environmental decoherence, while simultaneously allowing that information to interact with the classical spacetime geometry required for gravitational effects. The technical challenges involved in achieving such control exceed anything currently possible in quantum information science. The energy scales present another formidable barrier. While quantum computers can manipulate information using relatively modest amounts of energy, creating macroscopic gravitational effects would require energy densities that approach the fundamental limits of what spacetime itself can contain. The transition from quantum information processing to gravitational engineering would require bridging energy scales that span dozens of orders of magnitude. Yet these quantum experiments have revealed something profound about the relationship between information and geometry. The protocols used to create holographic wormholes in quantum computers bear striking mathematical similarities to the geometric requirements for stable spacetime tunnels. This suggests that the information theoretic and gravitational aspects of wormhole physics might be more deeply connected than previously imagined. The connection between quantum information and spacetime geometry has led physicists to reconsider fundamental questions about the nature of reality itself. If spacetime emerges from quantum information rather than being a fundamental backdrop for physical processes, then engineering spacetime might be equivalent to programming quantum computers on cosmic scales. The universe itself might be a vast information processing system where spacetime geometry represents the hardware and quantum fields represent the software. This information theoretic perspective on gravity has profound implications for wormhole construction. Instead of requiring exotic matter with negative energy density, wormholes might be created by manipulating quantum information in ways that naturally produce the geometric effects needed for spacetime tunnels. The exotic matter would emerge from quantum field configurations rather than needing to be independently created and positioned. But translating these insights into practical wormhole construction faces obstacles that extend far beyond current technological capabilities. The quantum error correction needed to maintain coherent quantum information across macroscopic distances would require computational resources that dwarf anything currently conceivable. Every quantum bit involved in the wormhole would need to be protected from environmental noise, while simultaneously participating in the collective quantum state that produces gravitational effects. The computational complexity of simulating even modest wormhole geometries stretches the limits of theoretical computer science. Classical computers cannot efficiently simulate quantum systems beyond a few dozen particles, and quantum computers face their own limitations when dealing with the highly entangled quantum states required for holographic wormhole construction. The information processing requirements for maintaining a stable wormhole might exceed the computational capacity of any physical system that could fit within the wormhole itself. The temporal aspects of holographic wormholes introduce additional layers of complexity that challenge our understanding of causality and information flow. Quantum information can be processed in ways that seem to violate classical notions of temporal order, with quantum circuits that appear to operate with indefinite causal structure. If macroscopic wormholes inherit these properties from their quantum information origins, they might enable forms of time travel that are even more exotic than those predicted by classical general relativity. The measurement problem that plagues quantum mechanics becomes particularly acute when applied to wormhole physics. Quantum systems exist in superpositions of multiple states until observed, at which point they collapse into definite configurations. But a macroscopic wormhole would presumably need to maintain a definite geometric configuration to allow passage of classical objects. The transition from quantum superposition to classical geometry would require measurement processes that are not well understood in the context of gravitational systems. Recent theoretical work has explored whether quantum measurement itself might play a fundamental role in spacetime geometry. Some interpretations of quantum mechanics suggest that conscious observation is necessary to collapse quantum superpositions into definite states. If spacetime geometry depends on quantum information, then the presence of conscious observers might be necessary to maintain stable wormhole configurations. This would create a profound connection between consciousness and the structure of spacetime itself. The implications extend to questions about whether artificial intelligence systems could serve as observers capable of maintaining wormhole stability. If quantum measurement requires some form of information integration or conscious awareness, then the design of wormhole control systems might need to incorporate features that we typically associate with consciousness rather than mere computation. The boundary between physics and philosophy becomes increasingly blurred when dealing with systems that operate at the intersection of quantum mechanics, gravity, and information theory. The search for practical applications of holographic wormhole physics has led researchers to explore connections with quantum communication and cryptography. While full-scale wormhole construction remains far beyond current capabilities, the quantum protocols used to create holographic wormholes might have immediate applications in quantum information science. These protocols could potentially enable new forms of quantum error correction or quantum cryptographic systems that are more robust than current approaches. The development of quantum networks, which would connect quantum computers around the world through quantum communication channels, might benefit from insights gained from holographic wormhole research. The mathematical techniques used to maintain quantum coherence across holographic wormholes could inform the design of quantum repeaters and quantum routers needed for large-scale quantum networks. But the ultimate goal of macroscopic wormhole construction would require advances that go far beyond incremental improvements in quantum technology. We would need fundamental breakthroughs in our understanding of quantum gravity, exotic matter, and the relationship between information and spacetime geometry. These breakthroughs might require experimental access to energy scales and spacetime curvatures that are currently accessible only in the most extreme astrophysical environments. The search for natural wormholes in the universe has intensified as our observational capabilities improve. While no confirmed wormhole detections have been made, astronomers are developing new techniques for identifying the gravitational signatures that traversable wormholes would create. The gravitational lensing effects produced by wormholes would differ subtly from those created by black holes or other conventional massive objects. Future space-based gravitational wave detectors might be sensitive enough to detect the characteristic signals produced by matter falling through natural wormholes. These signals would provide our first direct observational evidence of whether traversable wormholes exist in nature, potentially revealing whether the universe has already solved the engineering challenges that we find so daunting. The possibility that advanced extraterrestrial civilizations might have already constructed wormhole networks adds urgency to our search for such structures. A galaxy-spanning civilization with access to wormhole technology could establish transportation and communication networks that would be virtually invisible to civilizations limited to conventional physics. The absence of obvious signs of such networks might indicate either that wormhole construction is impossible or that advanced civilizations choose not to reveal their presence through such activities. The sociological implications of discovering natural or artificial wormholes would be profound. Confirmation that traversable wormholes exist would prove that the fundamental barriers we've identified can somehow be overcome, potentially accelerating human efforts to develop similar technologies. The knowledge that faster-than-light travel is possible would transform our perspective on humanity's cosmic future and our potential for interstellar exploration. The environmental consequences of wormhole construction would need careful consideration, even if the technical obstacles could be overcome. The exotic matter required for classical wormhole construction might need to be harvested from natural sources, potentially depleting cosmic resources or disrupting natural processes on galactic scales. The gravitational waves and radiation produced during construction could affect nearby star systems or interfere with other civilizations. The ethical frameworks needed to govern wormhole construction would require unprecedented international cooperation and long-term thinking. The decisions made during wormhole development could affect the entire future of human civilization and potentially other species throughout the galaxy. The responsibility for making such decisions wisely would exceed anything our species has previously encountered. The timeline for potential wormhole construction stretches far beyond current planning horizons. Even the most optimistic scenarios would require centuries of fundamental research followed by millennia of technological development. The institutional continuity needed to sustain such long-term projects would challenge our current models of scientific and technological development. The educational and cultural changes needed to support wormhole research would be equally challenging. Training the scientists and engineers needed for such projects would require educational systems designed to cultivate understanding that spans multiple scientific disciplines. The cultural values needed to sustain multi-generational research projects would need to balance ambition with patience, vision with realism. As we stand at the threshold of the quantum information age, the mathematical connections between quantum mechanics and gravity offer tantalizing hints that the universe might be more malleable than we previously imagined. The holographic principle suggests that reality itself might be a kind of cosmic information processing system where space-time geometry emerges from deeper layers of quantum information. The journey from today's modest quantum computers to hypothetical wormhole construction represents one of the most ambitious technological challenges our species could undertake. Success would require not just advances in physics and engineering, but fundamental changes in how we organize scientific research, allocate resources, and think about our place in the cosmic order. The questions raised by wormhole physics force us to confront the deepest mysteries of existence. They challenge us to think beyond the limitations of our current understanding and consider what might be possible for intelligence armed with complete knowledge of the laws that govern reality. Whether such knowledge could ever be translated into practical wormhole construction remains one of the most profound, open questions in science. The universe continues to reveal its secrets through the patient work of scientists and engineers who push the boundaries of human knowledge. Each quantum computing experiment brings us marginally closer to understanding the deep connections between information, gravity, and the structure of spacetime itself. The answers we seek may transform not just our understanding of physics, but our conception of what it means to be intelligent beings in a cosmos that might be far stranger and more wonderful than we ever dared imagine. The cosmic tunnels that Einstein and Rosen first glimpsed in their equations nearly a century ago remain as mysterious and alluring as ever. Whether they represent impossible dreams or achievable goals may depend on discoveries that await us in the quantum laboratories and theoretical physics departments of the coming decades. The universe keeps its deepest secrets well guarded, but it continues to offer tantalizing clues to those bold enough to ask whether reality itself might someday yield to the power of human intelligence and determination. The theoretical landscape of wormhole physics becomes even more treacherous when we venture beyond the quantum realm into the practical engineering challenges that would face any civilization attempting to construct a traversable spacetime tunnel. The Einstein-Rosen bridges that emerge from the field equations represent only the mathematical foundation for what would be the most ambitious construction project ever conceived by intelligent beings. To understand the magnitude of these challenges, we need to examine the specific geometric requirements that make traversable wormholes possible in the first place. The original Einstein-Rosen solutions describe what physicists call non-traversable wormholes, structures that pinch off so rapidly that nothing, not even light, can pass through them before they collapse. These mathematical constructs connect two black hole singularities through a tunnel that exists for only an infinitesimal moment before spacetime itself severs the connection. The breakthrough came when physicists realized that certain modifications to the Einstein field equations could produce stable, traversable geometries. But these modifications come at a cost that challenges everything we understand about the behavior of matter and energy in our universe. The Morris Thorne wormhole, developed in the late 1980s, requires what physicists euphemistically call exotic matter, material with properties so strange that its very existence would overturn fundamental assumptions about how reality operates. Exotic matter isn't simply unusual or rare, it possesses negative energy density and negative pressure, properties that violate the energy conditions that govern all known forms of matter and energy. To grasp how radical this requirement is, consider that every particle, every photon, every field fluctuation we've ever observed contributes positive energy to its local region of spacetime. Exotic matter would do the opposite, creating regions where the energy density is less than that of empty vacuum. The physical implications of negative energy density extend far beyond simple arithmetic. Such matter would create repulsive gravitational effects, pushing spacetime apart rather than drawing it together as ordinary matter does. This repulsive gravity is precisely what's needed to prevent a wormhole throat from collapsing under its own gravitational attraction. The exotic matter would line the interior of the tunnel, creating an outward pressure that counteracts the inward pull of normal gravitational forces. But the quantities of exotic matter required boggle the imagination. Kip Thorne's calculations indicate that stabilizing a wormhole with a throat diameter of just 1 meter would require exotic matter with negative energy equivalent to the mass of Jupiter. That's nearly 2 times 10 to the 27th kilograms of matter with properties that may not exist anywhere in the observable universe. Scaling up to a wormhole large enough for human passage would require even more astronomical quantities of this hypothetical substance. The engineering precision required to maintain such exotic matter configurations would exceed anything attempted in human technology. The distribution of negative energy would need to be controlled with tolerances measured in fractions of atomic diameters across distances that could span light years. Any deviation from the precise geometric requirements could trigger catastrophic collapse or create spacetime instabilities that propagate throughout the surrounding region. The stability constraints become even more demanding when we consider the dynamic behavior of wormhole geometries. Unlike static structures, such as bridges or buildings, wormholes would exist in a state of constant gravitational tension, with exotic matter continuously working to prevent collapse. while normal matter and radiation passing through the tunnel create perturbations that could destabilize the entire structure. Maintaining equilibrium would require active control systems capable of adjusting the exotic matter distribution in real time as conditions change. The causality implications of traversable wormholes introduce paradoxes that strike at the heart of our understanding of time and free will. If a wormhole connects two regions of space-time that are separated not just by distance, but by time, then travel through the tunnel could enable journeys into the past. The relativistic effects that govern how time passes in different gravitational fields could create situations where the two mouths of a wormhole exist at different temporal coordinates. Consider a scenario where one mouth of a wormhole remains stationary, while the other is accelerated to near the speed of light and then returned to its original location. The time dilation effects of special relativity would cause the travelling mouth to age more slowly than its stationary partner. When the mouths are reunited, they would no longer be synchronized in time. A traveller entering the stationary mouth and exiting through the previously accelerated mouth would emerge at an earlier time than when they began their journey. Such closed time-like curves create logical paradoxes that threaten the consistency of physical law itself. The grandfather paradox, where a time traveller prevents their own birth, represents just one example of the contradictions that backward time travel could create. The possibility of information travelling into its own past could enable violations of causality that would make rational prediction of future events impossible. Stephen Hawking proposed that the universe might possess built-in mechanisms to prevent such paradoxes from occurring. His chronology protection conjecture suggests that quantum effects would automatically destroy any configuration of matter and energy that could enable backward time travel. As space-time approaches the geometry needed for closed time-like curves, quantum field fluctuations would be amplified to such extreme energies that they would obliterate the incipient time machine before it could become operational. The quantum vacuum, far from being empty space, seethes with virtual particle pairs that constantly appear and annihilate according to the uncertainty principle of quantum mechanics. In the curved space-time near a potential time machine, these quantum fluctuations could be blue-shifted to arbitrarily high energies, creating a firewall of destructive radiation that would prevent the formation of closed time-like curves. Nature itself might be equipped with an immune system against temporal paradoxes, but the chronology protection conjecture remains unproven, and some solutions to the equations of general relativity seem to permit stable closed time, like curves under certain exotic conditions. The Alcubierre warp drive, which theoretically allows faster-than-light travel by contracting spacetime in front of a spacecraft and expanding it behind, could potentially be used to create closed time, like curves, if the spacecraft's trajectory were carefully designed. The quantum gravity constraints that govern physics at the smallest scales introduce additional layers of complexity that could fundamentally alter our understanding of wormhole behavior. At distances approaching the Planck length, roughly 10 to the minus 35 meters, the smooth geometry of classical spacetime dissolves into quantum foam, where the very concepts of distance and duration become uncertain. In this realm, virtual wormholes might spontaneously appear and disappear according to quantum mechanical principles, creating a dynamic network of microscopic spacetime connections that permeates the universe at the smallest scales. These quantum wormholes would be far too small and short-lived to allow macroscopic passage, but they might play crucial roles in fundamental physics processes such as particle interactions and field propagation. The challenge of scaling quantum wormholes to macroscopic dimensions involves bridging energy scales that span more than 60 orders of magnitude. The quantum effects that permit microscopic wormholes operate at energies near the Planck scale, roughly 10 to the 19th billion electron volts. Creating macroscopic wormholes would require maintaining coherent quantum states while simultaneously producing gravitational effects that operate at much lower energy scales. String theory, which attempts to unify quantum mechanics and general relativity by treating fundamental particles as vibrating strings in higher dimensional space, offers tantalizing hints about how such scale bridging might be possible. Some string theory models predict that extra spatial dimensions could be compactified in ways that make quantum gravitational effects accessible at lower energies than previously thought possible. Loop quantum gravity provides an alternative approach that treats spacetime itself as composed of discrete quantum units rather than a smooth continuum. In this picture, the throat of a wormhole would be constructed from quantum geometric building blocks, whose properties might fundamentally constrain the kinds of structures that can exist. The granular nature of quantum spacetime could impose limits on wormhole stability that aren't captured by classical general relativity. The information paradoxes that plague black hole physics extend to wormhole construction in ways that could fundamentally limit their practical utility. If information cannot be destroyed, as quantum mechanics requires, then what happens to quantum information that enters a wormhole? The no-cloning theorem of quantum mechanics forbids perfect duplication of quantum states, but wormholes might seem to allow information to exist simultaneously at both mouths of the tunnel. Recent work on the firewall paradox suggests that quantum effects might create walls of high-energy particles at the horizons of black holes, making them lethal to any observer who attempts to cross the boundary. Similar effects might occur at wormhole throats, creating barriers of destructive radiation that would prevent safe passage regardless of how carefully the exotic matter is engineered. The holographic principle offers a potential resolution to some of these information paradoxes by suggesting that all information in a volume of spacetime can be encoded on its boundary surface. If wormholes operate according to holographic principles, then the information passing through the tunnel might be encoded on the throat surface rather than traveling through the interior volume. This could eliminate some paradoxes while creating new challenges for understanding how holographic information encoding would affect travelers. The thermodynamic properties of wormholes introduce constraints that could make their operation prohibitively expensive from an energy perspective. If wormholes possess temperature and entropy like black holes, then the second law of thermodynamics would require that any information or matter passing through the tunnel must increase the total entropy of the universe. The energy cost of entropy production could exceed even the enormous energy requirements for exotic matter creation. Some calculations suggest that the thermodynamic cost of sending a single bit of information through a wormhole could require energy comparable to that contained in the mass of an elementary particle. For macroscopic objects, the entropy production costs could exceed the rest mass energy of the object being transported, making wormhole travel less efficient than simply destroying the object at one location and reconstructing it at another. The gravitational wave signatures produced by wormhole construction and operation would be detectable across vast distances, potentially revealing the presence of such structures to any civilization with sufficiently sensitive instruments. The exotic matter required for wormhole stabilization would create gravitational field patterns unlike anything produced by conventional matter, generating characteristic wave signatures as objects pass through the tunnel. Future gravitational wave detectors, potentially including space-based interferometers with baseline lengths measured in millions of kilometers, might be sensitive enough to detect these signals from natural wormholes if they exist in our galaxy. The detection of such signals would provide our first direct observational evidence that traversable wormholes are possible, potentially revolutionizing our understanding of fundamental physics. The absence of detectable wormhole signatures in current gravitational wave observations places constraints on how common such structures might be in our local cosmic neighborhood. If advanced civilizations elsewhere in the galaxy had constructed wormhole networks, the gravitational wave signatures would likely be visible to our current generation of detectors. The silence might indicate either that wormhole construction is impossible or that such projects are beyond the capabilities of any civilization in our galactic vicinity. The material science challenges involved in wormhole construction would require advances that dwarf anything achieved in human technology. Any structural components that support the exotic matter configuration would need to withstand stresses that exceed the binding energy of atomic nuclei. The materials would need to maintain their properties under conditions of extreme spacetime curvature, where the normal rules of condensed matter physics break down completely. The exotic matter itself would need to be contained and manipulated using techniques that violate our current understanding of how matter and energy behave. Negative energy densities would create repulsive forces that would naturally disperse the exotic matter unless it were somehow constrained by even more exotic fields or boundary conditions. The engineering systems needed to maintain such configurations would themselves require materials and energy sources that don't exist in our current technological repertoire. The power requirements for wormhole operation could exceed the energy output of entire stars. Some estimates suggest that maintaining a human-sized wormhole would require continuous energy input equivalent to the power generated by multiple stellar cores undergoing nuclear fusion. The infrastructure needed to collect, store, and distribute such enormous energy flows would represent a technological achievement that transcends anything conceivable within our current scientific paradigm. The quality control and safety protocols for wormhole construction would need to address failure modes that could potentially damage the structure of spacetime itself. Unlike conventional engineering projects, where failures affect only local regions, a catastrophic wormhole collapse could create spacetime defects that propagate at the speed of light, potentially affecting vast volumes of the surrounding universe. The risk assessment for such projects would need to consider consequences that extend across cosmic scales and geological time periods. A single engineering error during wormhole construction could create cascading failures that affect the gravitational environment of entire star systems. The responsibility for making such projects safe would require understanding physics at levels that far exceed our current knowledge. The regulatory frameworks needed to govern wormhole construction would challenge every existing model of international cooperation and technological oversight. The global implications of wormhole technology would require unprecedented levels of coordination between nations, scientific institutions, and potentially other civilizations, if contact were established during the development process. The economic models that would govern access to wormhole technology present challenges that extend far beyond conventional transportation economics. The energy costs involved in construction and operation might limit access to only the most advanced and wealthy civilizations, creating new forms of inequality based on access to space-time engineering capabilities. The social and cultural implications would be equally profound. Instantaneous travel between distant locations would fundamentally alter human concepts of distance, nationality, and cultural identity. The psychological adaptation required to function in a universe where location becomes arbitrary might exceed our species' capacity for adjustment to rapid technological change. The timeline for potential wormhole development stretches far beyond any conventional planning horizon. Even the most optimistic scenarios would require centuries of fundamental research followed by millennia of technological development. The institutional continuity needed to sustain such long-term projects would challenge our current models of scientific organization and resource allocation. The educational systems needed to train wormhole engineers would require curricula that span multiple scientific disciplines while maintaining depth in each area. The interdisciplinary knowledge needed to understand quantum gravity, exotic matter physics, and cosmic scale engineering would exceed the educational capacity of any individual, requiring new models of collaborative expertise and distributed knowledge systems. As we contemplate these staggering challenges, the question of whether wormholes can ever be built becomes inseparable from deeper questions about the nature of intelligence itself. Are there fundamental limits to what conscious beings can achieve through understanding and manipulating the laws of physics? Or might sufficiently advanced civilizations develop capabilities that transcend every obstacle we've identified? The answer may depend on discoveries that await us in the quantum laboratories and theoretical physics departments of the coming centuries. Each advance in our understanding of quantum gravity brings us marginally closer to comprehending whether the universe permits the kinds of spacetime engineering that wormhole construction would require. The mathematical elegance of Einstein's equations continues to suggest possibilities that challenge our assumptions about what might be achievable for intelligence armed with complete knowledge of physical law. The cosmic tunnels that first emerged from theoretical calculations nearly a century ago remain as mysterious and compelling as ever. Whether they represent achievable goals or impossible dreams may ultimately depend on whether the universe's deepest laws permit consciousness to transcend the constraints of space and time. The journey toward answering that question continues to drive research at the very frontiers of human knowledge, where mathematics and imagination converge in the quest to understand what might be possible in a cosmos that consistently proves stranger and more wonderful than we dare to imagine. Imagine the intersection of theoretical possibility and engineering reality becomes even more stark when we examine the specific mechanisms by which wormholes might be artificially created in the first place. Unlike the natural formation of black holes through stellar collapse, wormholes would almost certainly require deliberate construction, using technologies that manipulate the fundamental structure of spacetime itself. The most promising theoretical approaches involve starting with existing gravitational anomalies and modifying their geometry through precise application of exotic matter. Some physicists have proposed that microscopic wormholes might naturally exist in the quantum foam that permeates empty space at the smallest scales. These theoretical structures, far smaller than atomic nuclei, would appear and disappear in timeframes measured in units of Planck time, roughly 10 to the minus 43 seconds. If such quantum wormholes do exist, the challenge would be to capture one during its brief existence and inflate it to macroscopic dimensions while simultaneously stabilizing it with exotic matter. The process would be analogous to blowing up a soap bubble, except the bubble would be made of spacetime itself, and the air would be matter with properties that violate every known energy condition. The inflation process would require extraordinary precision in timing and energy application. The exotic matter would need to be injected into the quantum wormhole at precisely the moment it forms, in exactly the right configuration to prevent immediate collapse while providing the energy needed for expansion. The window of opportunity would be measured in units of time so small that light could travel only a fraction of the distance across an atomic nucleus. Alternative construction scenarios involve creating artificial spacetime curvature through the manipulation of electromagnetic fields or gravitational wave interactions. Some theoretical models suggest that focused beams of coherent gravitational waves might be able to create localized distortions in spacetime geometry that could serve as seeds for wormhole formation. But generating gravitational waves with the required intensity and precision would require energy sources and focusing mechanisms that dwarf our current technological capabilities. The laser interferometer gravitational wave observatories that detected merging black holes and neutron stars represent humanity's first tentative steps toward gravitational wave technology. These instruments can detect space-time distortions smaller than 1/10,000th the width of a proton. But creating gravitational waves rather than simply detecting them would require technologies that could manipulate masses comparable to stars with precision measured in fractions of atomic diameters. Electromagnetic approaches to space-time manipulation face even more daunting challenges. While electric and magnetic fields can create measurable effects on spacetime curvature through their energy density, the field strengths required for significant geometric modification would exceed anything achievable with conventional technology. The magnetic fields would need to be millions of times stronger than those created in the most powerful laboratory electromagnets, sustained across volumes that could encompass entire planetary systems. The power distribution networks needed to support such field generation would themselves represent unprecedented engineering challenges. Superconducting cables capable of carrying the required currents would need to maintain zero electrical resistance under conditions of extreme magnetic field strength and spacetime curvature. The energy storage systems would need to accumulate and release power on scales comparable to the total energy output of major stars. Even if the initial construction challenges could be overcome, maintaining a stable wormhole would require continuous active control systems that monitor and adjust the exotic matter distribution in response to changing conditions. Every particle of ordinary matter that passes through the tunnel would create gravitational perturbations that could destabilize the entire structure, if not immediately compensated by adjustments to the exotic matter configuration. The feedback control systems would need to operate faster than light can travel through the wormhole to prevent instabilities from propagating and causing catastrophic collapse. This apparent violation of special relativity might be resolved through quantum entanglement effects between the exotic matter particles, allowing instantaneous communication between different parts of the wormhole structure. But exploiting quantum entanglement for macroscopic control systems would require maintaining quantum coherence under conditions where such coherence has never been observed. The navigation challenges for wormhole travel introduce complexities that extend far beyond conventional transportation systems. Unlike traveling between fixed points connected by roads or flight paths, wormhole travel would involve moving between regions of spacetime that might have completely different physical properties. The gravitational fields, electromagnetic environments, and even the fundamental constants of physics could vary between the two mouths of the tunnel. Travelers would need protection from tidal forces that could vary dramatically along the length of the wormhole. The differential gravitational effects that stretch and compress objects in strong gravitational fields would operate according to the exotic geometry of the tunnel interior. Conventional spacecraft shielding would be useless against forces that arise from the curvature of spacetime itself. The radiation environment inside a wormhole would be unlike anything encountered in normal space travel. As photons and charged particles pass through the tunnel, they would interact with the exotic matter lining the throat in ways that could generate high-energy radiation. The blue shifting effects that concentrate light as it falls into gravitational wells could transform ordinary starlight into deadly gamma rays within the confined geometry of the wormhole interior. Atmospheric pressure and life support systems would face challenges that have no analogy in conventional engineering. The exotic matter required for wormhole stabilization might interact with ordinary matter in ways that could contaminate breathing air or interfere with electronic systems. Backup life support systems would need to function reliably in environments where the normal laws of thermodynamics might be modified by the presence of negative energy densities. Communication systems would need to account for the complex electromagnetic propagation effects within the wormhole geometry. Radio signals might be bent, focused, or dispersed in unpredictable ways as they interact with the curved spacetime and exotic matter. Emergency communication with the outside universe might be impossible once travelers enter the tunnel, creating safety challenges that have no precedent in human exploration. The psychological effects of wormhole travel could prove as challenging as the physical hazards. The human mind evolved to navigate three-dimensional space at speeds much slower than light, with gravitational effects so weak they're barely perceptible in everyday life. The experience of traveling through a tunnel in space-time where the normal rules of geometry and causality might be suspended, could overwhelm sensory and cognitive systems that have no evolutionary preparation for such conditions. Motion sickness represents just the beginning of potential neurological complications. The brain's spatial orientation systems depend on consistent gravitational references and visual cues that follow predictable geometric relationships. Inside a wormhole, where spacetime itself is folded and twisted, these systems might receive contradictory information that could trigger disorientation, nausea, or more severe neurological symptoms. The time dilation effects that would inevitably accompany wormhole travel could create psychological trauma that persists long after the journey ends. Travelers might experience only minutes of subjective time, while external observers measure hours, days, or years passing. The social and emotional consequences of such temporal displacement could be devastating for individuals who return to find that their entire social context has aged or changed beyond recognition. These human factors considerations highlight the profound difference between theoretical possibility and practical implementation. Even if all the physics and engineering challenges could be solved, wormhole travel might remain limited to automated probes or artificial intelligence systems that lack the psychological vulnerabilities that would make human passage problematic. The economic analysis of wormhole construction reveals cost structures that challenge conventional models of technological development and deployment. Unlike conventional transportation infrastructure, where costs scale roughly with the physical size and complexity of the system, wormhole costs would be dominated by the exotic matter requirements that scale exponentially with tunnel diameter. A wormhole large enough to accommodate a single photon might require exotic matter equivalent to the mass of a small asteroid. Scaling up to allow passage of a spacecraft would require exotic matter comparable to planetary masses. The economic value of instantaneous interstellar travel would need to justify energy expenditures that exceed the total economic output of entire civilizations. The development timeline for wormhole technology would span centuries or millennia, requiring economic planning and resource allocation on scales that exceed any historical precedent. The initial research phases alone would require international cooperation and funding commitments that dwarf current space exploration budgets. The infrastructure development needed to support exotic matter production and spacetime engineering would represent a civilizational undertaking comparable to the construction of entire technological societies. Risk management for such investments would require assessing potential returns across timescales, where technological and social change could render the entire project obsolete before completion. The opportunity costs of dedicating such enormous resources to wormhole development would need to be weighed against alternative uses that could provide more immediate benefits to human welfare and scientific advancement. The intellectual property frameworks that would govern wormhole technology present challenges that extend far beyond current legal and economic models. The fundamental physics discoveries needed for wormhole construction would likely emerge from international research collaborations involving scientists from multiple nations and institutions. Determining ownership and control of technologies that could reshape the strategic balance of power on Earth would require unprecedented levels of international cooperation and dispute resolution. Patent systems designed for conventional technologies would be inadequate for innovations that manipulate the fundamental structure of spacetime. The enforcement mechanisms that protect intellectual property rights would become meaningless in a universe where wormhole technology allows instantaneous access to any location. New legal frameworks would need to address questions of jurisdiction and sovereignty that have no precedent in human law. The environmental impact assessments for wormhole construction would need to consider effects that operate across cosmic scales and geological time periods. The exotic matter required for construction might need to be harvested from natural sources, potentially depleting cosmic resources or disrupting astrophysical processes that affect entire galactic regions. The gravitational wave emissions produced during construction and operation would propagate across the galaxy at the speed of light, potentially interfering with natural astronomical processes or the activities of other civilizations. The responsibility for such far-reaching consequences would require ethical frameworks that extend beyond anthropocentric concerns to consider the welfare of cosmic processes and potentially other forms of intelligence. Waste management for wormhole construction would involve dealing with byproducts that might include exotic forms of matter and energy with properties that remain stable across cosmic timescales. Unlike conventional industrial waste that eventually decomposes or can be safely contained, exotic matter waste might persist indefinitely and could interact with future technological developments in unpredictable ways. The decommissioning procedures for obsolete wormholes would present challenges that have no analogy in current engineering practice. Simply abandoning a wormhole structure could create permanent spacetime anomalies that affect the gravitational environment for billions of years. Safe disposal would require technologies and procedures that might be even more complex than the original construction process. Quality assurance for wormhole construction would require testing and validation procedures that operate under conditions where failure could affect the structure of spacetime itself. Unlike conventional engineering where prototypes can be built and tested incrementally, wormhole construction might permit only one attempt at full-scale implementation. The testing procedures would need to validate theoretical models using computer simulations and scaled experiments that might not capture all the relevant physics. The certification processes that ensure safety and reliability would need to account for failure modes that could propagate across interstellar distances. Regulatory agencies would require expertise in quantum gravity, exotic matter physics, and cosmic scale engineering that far exceeds the knowledge base of any current human institution. International standards for wormhole construction would need to be developed before any construction begins, requiring consensus among scientific communities that might have fundamentally different approaches to the underlying physics. Emergency response procedures would need to address scenarios where wormhole instabilities could affect entire solar systems. The response capabilities would need to include technologies for containing or neutralizing exotic matter configurations that could persist for cosmic timescales. Evacuation procedures might need to account for populations spread across multiple star systems connected by wormhole networks. The training requirements for wormhole engineers and operators would exceed any current educational model. The interdisciplinary knowledge needed would span quantum mechanics, general relativity, exotic matter physics, cosmic scale engineering, and potentially fields of study that don't yet exist. The expertise development timeline could span multiple human generations, requiring educational institutions and knowledge preservation systems designed for unprecedented longevity. Simulation and modeling capabilities would need to accurately represent physics that operates beyond the standard model and general relativity. The computational requirements for modeling quantum gravity, effects in exotic matter configurations, might exceed the information processing capacity of any conceivable physical system. Verification of theoretical predictions would require experimental capabilities that can recreate conditions similar to those found in the most extreme astrophysical environments. As we survey this landscape of challenges that span from fundamental physics to practical engineering to social organization, the question of whether wormholes can ever be built becomes inseparable from deeper questions about the nature and limits of intelligence itself. The obstacles we've identified might represent fundamental barriers that no amount of technological advancement can overcome, or they might simply reflect the limitations of our current understanding and capabilities. The history of human technological development is filled with examples of seemingly impossible challenges that were eventually overcome through combinations of scientific breakthrough, engineering innovation, and social organization. Powered flight, space travel, nuclear energy, and quantum computers all seemed impossible until they became routine. But wormhole construction might represent a qualitatively different category of challenge that transcends anything previously attempted by technological civilizations. The energy scales, precision requirements, and temporal commitments involved in wormhole construction might exceed the physical and organizational capabilities of any intelligence bounded by the laws of physics. The exotic matter requirements might violate fundamental principles that prevent such configurations from existing in our universe. The causality paradoxes might represent logical impossibilities that no amount of clever engineering can resolve. Yet the mathematical elegance of Einstein's equations continues to suggest possibilities that challenge our assumptions about what might be achievable. Each advance in our understanding of quantum gravity and exotic matter brings us marginally closer to comprehending whether the universe permits the kinds of spacetime engineering that wormhole construction would require. The theoretical framework exists, even if the practical implementation remains far beyond our current reach. The pursuit of wormhole technology represents more than just an ambitious engineering project. It embodies humanity's deepest aspirations to transcend the constraints that bound us to a single world in a vast universe filled with wonders we can observe but not directly explore. The journey toward understanding whether such aspirations can ever be realized continues to drive research at the frontiers of physics, where the boundaries between the possible and impossible remain tantalizingly unclear. Whether the cosmic tunnels that first emerged from Einstein's equations nearly a century ago represent achievable goals or eternal mysteries may ultimately depend on discoveries that await us in the quantum laboratories and theoretical physics departments of the coming centuries. The universe continues to reveal its secrets to those bold enough to ask whether consciousness and intelligence might someday command sufficient understanding and capability to reshape the very fabric of space-time itself. The answer to that question will determine not just our technological future, but our fundamental place in a cosmos whose deepest laws may either permit or forbid the transcendence of space and time through the power of directed intelligence. The practical reality of wormhole construction would require confronting a cascade of interconnected challenges that extend far beyond the exotic matter requirements we've explored. Each solution creates new problems, each breakthrough reveals deeper mysteries, and each step forward seems to demand exponentially greater resources and understanding. Consider the fundamental issue of how one would even begin to construct a wormhole in practice. The theoretical models that describe stable, traversable geometries assume that exotic matter can somehow be positioned with perfect precision throughout the tunnel structure. But how would such positioning be achieved when the matter itself possesses properties that defy every principle of engineering we've ever developed? Exotic matter with negative energy density would naturally repel itself, creating dispersive forces that would scatter the material the moment it's created. Unlike ordinary matter that can be contained by electromagnetic fields or mechanical structures, exotic matter would require containment mechanisms that themselves violate conventional physics. We would need to develop technologies that can manipulate matter with properties we don't understand using forces that may not exist. The manufacturing processes for exotic matter production would need to operate under conditions that push every known physical principle to its breaking point. The Casimir effect demonstrates that quantum mechanics can create tiny regions of negative energy density between conducting plates separated by distances smaller than the wavelength of light. But scaling this effect up to produce the macroscopic quantities needed for wormhole construction would require manufacturing tolerances that make precision atomic manipulation seem crude by comparison. The quality control requirements would be absolute. A single imperfection in the exotic matter distribution could propagate through the wormhole geometry like a crack spreading through glass, potentially causing instantaneous collapse or creating spacetime defects that persist indefinitely. The inspection and testing procedures would need to verify the properties of matter that behaves in ways contrary to every measurement technique we've developed for normal materials. Storage and transportation of exotic matter would present challenges that have no precedent in materials science. Containers that could hold matter with negative energy density would themselves need to be made from materials with properties that violate energy conditions. The logistics of moving such materials from production facilities to construction sites would require developing entirely new categories of industrial equipment and safety protocols. The construction sequence itself would need to unfold with choreographed precision across scales ranging from quantum mechanical to astronomical. The exotic matter would need to be positioned while simultaneously creating the spacetime curvature that defines the wormhole geometry. It's a chicken and egg problem where each component depends on the other for its existence, requiring construction techniques that have no analogy in conventional engineering. Imagine trying to build a suspension bridge where the cables need to be in place before the towers can be constructed, but the towers need to exist before the cables can be suspended. Now multiply that complexity by factors that account for quantum uncertainty, relativistic effects, and materials that actively resist being confined in the required configurations. The construction would need to proceed according to sequences where causality itself becomes ambiguous. The workforce required for such construction would need training in disciplines that don't yet exist. Traditional engineering education assumes materials that follow predictable stress-strain relationships and forces that obey conservation laws. Wormhole engineers would need to understand how to work with matter that creates its own gravitational repulsion and energy sources that violate thermodynamics. The educational infrastructure to develop such expertise would require decades of development before construction could even begin. Safety protocols would need to address failure modes that could affect the stability of spacetime across interstellar distances. A construction accident involving exotic matter wouldn't simply endanger the immediate work site, but could create gravitational anomalies that propagate at light speed throughout the surrounding galaxy. The emergency response capabilities would need to include technologies for containing or neutralizing spacetime defects that could persist for billions of years. The coordination requirements would exceed anything attempted in human history. Every aspect of the construction would need to be synchronized, with precision measured in units of Planck time, while spanning distances that could encompass multiple solar systems. Communication delays between different parts of the construction site could exceed the time available for making critical adjustments to prevent catastrophic instabilities. Project management for wormhole construction would require planning tools that can account for relativistic effects, quantum uncertainties, and the possibility that the fundamental laws of physics might need revision during the development process. The timeline uncertainties would span orders of magnitude, with critical path dependencies that involve discoveries in theoretical physics that may or may not prove possible. The resource allocation decisions would need to balance competing demands that operate on completely different scales. Quantum mechanical effects might require investments in experimental facilities that cost more than current national economies, while the exotic matter production might consume energy equivalent to the total output of multiple stellar cores. The opportunity costs would include foregone advances in every other area of science and technology. Financing mechanisms for such projects would challenge every existing model of investment and economic planning. The development timeline could span millennia, requiring financial institutions and governance structures designed for unprecedented longevity. The return on investment calculations would need to account for benefits that might not be realized for hundreds of generations, requiring economic theories that extend far beyond current planning horizons. International cooperation requirements would exceed anything achieved in human political history. The energy resources needed for exotic matter production would require coordination between spacefaring civilizations that might span multiple star systems. The governance frameworks would need to address questions of sovereignty and jurisdiction that have no precedent when the construction site exists partially outside normal three-dimensional space. Technology transfer and knowledge-sharing protocols would need to ensure that critical information remains accessible across the centuries or millennia required for completion. The institutional memory requirements would exceed the lifespan of any current human organization, requiring knowledge preservation systems that can maintain technical accuracy across timescales where entire scientific paradigms might change. Quality assurance for the final product would require testing procedures that validate performance under conditions that can't be fully reproduced until the wormhole is actually completed. The acceptance criteria would need to specify tolerances for spacetime geometry that can't be measured using any existing instrumentation. The warranty and maintenance agreements would need to address responsibilities that extend across cosmic timescales. Decommissioning procedures would need to address the possibility that wormhole technology might become obsolete before the construction is completed. The safe disposal of partially completed exotic matter configurations might require more advanced technology than the original construction, creating planning paradoxes where the end-of-life procedures need to be developed before the operational procedures are finalized. Environmental impact assessments would need to consider effects on astrophysical processes that operate across galactic scales. The gravitational wave emissions from construction activities would propagate throughout the local galaxy, potentially affecting stellar formation processes, planetary orbits, and the evolution of other star systems. The responsibility for such far-reaching consequences would require ethical frameworks that extend beyond any current environmental protection model. The scientific validation requirements would push experimental physics into regimes where current theoretical frameworks might prove inadequate. The exotic matter configurations needed for wormhole construction would exist in states that have never been observed in nature or laboratory settings. The measurement techniques needed to verify their properties would themselves need to operate using principles that might violate established physical laws. Computational modeling of wormhole construction would require simulations that accurately represent quantum gravity effects, exotic matter dynamics, and macroscopic spacetime curvature simultaneously. The computational complexity could exceed the information processing capacity of any physical system that could fit within the observable universe. The validation of such models would require experimental capabilities that can recreate conditions comparable to those found in the most extreme astrophysical environments. The interface between human psychology and wormhole technology would require addressing cognitive and emotional challenges that have no precedent in human experience. The construction workers and engineers would need to function effectively in environments where normal spatial relationships don't apply, and where the consequences of errors could affect the future evolution of entire galactic regions. Training simulators would need to accurately represent the experience of working with exotic matter and curved spacetime, while ensuring that trainees don't develop psychological disorders from exposure to environments that contradict fundamental human intuitions about space, time, and causality. The occupational health standards would need to address both physical and mental health effects of prolonged exposure to exotic physics phenomena. Cultural adaptation requirements would extend throughout human society as wormhole construction reshapes fundamental assumptions about distance, travel, and accessibility. The social institutions that depend on geographic isolation and transportation costs would need to evolve or face obsolescence. The psychological preparation would need to help entire populations adapt to living in a universe where instantaneous travel to distant galaxies becomes as routine as current intercontinental flight. The legal frameworks governing wormhole technology would need to address questions of jurisdiction and liability that transcend current models of international law. If a wormhole connects regions that exist in different temporal coordinates, which legal system would govern activities within the tunnel? How would contracts and property rights be enforced when the parties might exist at different points in time? Patent and intellectual property protections would become meaningless in a universe where wormhole technology allows instantaneous access to any location. The enforcement mechanisms that protect innovation and investment would need complete redesign to account for the possibility that competing technologies might be developed in temporal or spatial locations that are inaccessible to conventional legal authority. Criminal justice systems would face unprecedented challenges when investigating crimes that might involve evidence scattered across multiple star systems or different time periods. The forensic techniques needed to trace activities through wormhole networks would require investigative capabilities that extend far beyond current law enforcement methods. The economic implications would transform every aspect of human commerce and resource allocation. Transportation costs would become negligible for goods that could be moved instantaneously across galactic distances, but the energy costs of maintaining wormhole networks might exceed the value of most commodities. New economic models would need to account for markets where supply and demand operate according to principles that ignore geographical constraints. Labour markets would need to adapt to conditions where workers could commute instantaneously between jobs located on different planets or in different star systems. The social and psychological effects of such mobility could destabilize traditional community structures and cultural institutions that depend on geographical continuity. Tourism and recreation industries would face opportunities and challenges that dwarf current travel and hospitality sectors. The possibility of day trips to distant galaxies would create demand for services that have no current analogy, but the energy costs and safety requirements might limit access to only the most wealthy individuals or organizations. Educational systems would need to prepare students for careers that involve working with physics and technologies that contradict fundamental human intuitions about reality. The curriculum development would require integrating knowledge from fields that don't yet exist, while maintaining educational depth in established disciplines that remain relevant. Research methodologies would need evolution to address phenomena that operate across scales from quantum mechanical to cosmic, while involving materials and forces that may violate currently accepted physical principles. The peer review processes would need to evaluate claims about technologies that can't be independently verified using existing experimental capabilities. The philosophical implications would force reconsideration of fundamental questions about the nature of space, time, causality, and human purpose in the universe. Religious and spiritual traditions would need to adapt to cosmologies that include engineered spacetime structures and the possibility of causal loops that challenge linear concepts of divine purpose and moral responsibility. Art and literature would find inspiration in possibilities that expand human experience beyond anything previously imaginable, but would also face the challenge of creating meaningful expression for audiences whose fundamental relationship with space and time has been transformed by technology that makes science fiction seem conservative by comparison. As we contemplate this vast landscape of interconnected challenges, the question of whether wormholes can ever be built becomes inseparable from deeper questions about the ultimate limits of what intelligence can achieve within the constraints imposed by physical law. Each obstacle we've identified might represent a fundamental barrier that no amount of technological advancement can overcome, or it might simply reflect the current limitations of human knowledge and capability. The mathematical elegance of the solutions to Einstein's field equations continues to suggest that the universe might permit spacetime engineering on scales that dwarf our current imagination. But the practical implementation of such engineering would require not just technological advancement, but fundamental changes in how conscious beings organize themselves, allocate resources, and think about their relationship to the cosmos itself. The journey toward understanding whether wormhole construction represents an achievable goal or an eternal impossibility continues to drive research at the frontiers of human knowledge. Each advance brings us marginally closer to comprehending the ultimate question of whether intelligence armed with complete understanding of physical law might someday transcend the barriers that currently confine consciousness to single locations in space and time. The universe maintains its silence about whether such transcendence is possible, revealing its secrets only through the patient work of scientists and engineers who push the boundaries of understanding into realms where the distinction between the achievable and the impossible remains tantalizingly unclear. Whether the cosmic tunnels that Einstein and Rosen first glimpsed in their equations represent humanity's ultimate destiny or its most beautiful impossibility may depend on discoveries that await us in the laboratories and theoretical physics departments of the coming centuries. The answer will determine not just our technological future, but our fundamental understanding of what it means to be conscious beings in a universe whose deepest laws may either permit or forever prohibit the conquest of space and time through the directed application of intelligence, knowledge, and an audacity that matches the cosmic scale of the challenges we dare to contemplate. So here we stand, at the edge of one of science's most profound questions. Having journeyed through the mathematical poetry of Einstein-Rosen bridges and the mind-bending requirements of exotic matter that defies every intuition we've developed about reality. We've seen how the elegant solutions hidden within general relativity demand materials with negative energy density, engineering precision that makes atomic manipulation look crude, and energy scales that dwarf the output of entire civilizations. The stability challenges alone would require mastering spacetime geometry with quantum-level precision, while the causality paradoxes threaten to unravel the logical structure of physics itself. Add the quantum gravity constraints that operate at scales where our current theories break down completely, and wormhole construction emerges as perhaps the ultimate test of whether intelligence can transcend the fundamental barriers that govern cosmic evolution. Yet the mathematical framework exists. The equations permit these structures, quantum experiments hint at deep connections between information and geometry, and each advance in our understanding brings us marginally closer to comprehending whether the universe truly allows consciousness to reshape the fabric of space-time itself. Whether the cosmic tunnels that Einstein and Rosen first glimpsed in their calculations nearly a century ago represent humanity's greatest impossible dream or its most audacious achievable goal may ultimately depend on discoveries that await us in the quantum laboratories of tomorrow. The universe keeps its deepest secrets closely guarded, but it continues offering tantalizing clues to those bold enough to ask whether reality itself might someday yield to the power of directed intelligence and determination. Until next time, keep looking up at those distant stars, and remember that the greatest adventures in science often begin with the simplest question: what if?